What's going on, everyone? Welcome to my channel where I talk about finance and technology applications. And in this video, I'll be going over an LSTM, otherwise known as a long short-term memory model. Now, I'm already assuming that you checked out my two previous videos on the RNNs and the GRUs because both of their infrastructures, theory, are very similar to that of an LSTM. The LSTM was built on the RNNs and the GRU was built on the LSTM. Furthermore, the code in this video for LSTMs is built off of the code of the RNNs and GRUs. And before you forget, make sure you hit that like button and subscribe. It really helps out with the growth of this channel, and also you get to see more content on finance and technology applications. Similar to my previous videos, I'll be breaking up this video into two sections. The first section being the theory behind a LSTM, what each step within the LSTM resembles and symbolizes, and what it does. The second section, I'll just be focusing on the applications of an LSTM. How does it run? What type of inputs does it require? And I also will be comparing the results of an LSTM to a GRU and a recurrent neural network. So I created a deck that would just go through the LSTM illustrations and what you would typically see within the LSTM and how each component interacts with the other. So a little bit of background on what the LSTM is made for. Previously, the RNN, which was a very popular model back in the day, until it came across this vanishing gradient problem where the weights were not being updated correspondingly or iteratively, like it wasn't increasing or decreasing. It was either staying very still, meaning there's no change within the weights, or the weights were increasingly exponentially or decreasing, you name it. So that's also the exploding gradient problem. So the LSTM was created for that. Also the GRU was created for that as well. So these two properties effectively address the vanishing gradient problem. So when do you use the LSTM? Largely, the LSTM is a more complex model than the RNN and the GRU. So typically, if you have a huge data set with long sequences, then typically the LSTM retains memory longer than the GRU. And if your data were a little bit smaller, shorter sequences, then typically you would default to a GRU, because the GRU actually takes less amount of time to train because it has less parameters, and it typically has very similar results, but it really just depends on what type of data you are using. The LSTM is more computationally complex and therefore more powerful than the GRU, so it takes a little bit longer. But that's largely like the minute details between the two models. But then again, you always want to compare the two models or three models to see which has the best predictions and best bang for the buck, so to say. Now let's go to the architecture, where this is like a very high level overview, but we'll go a little bit more in depth as to what the LSTM is. But essentially the LSTM has three gates: the forget gate, input gate, and the output gate. And each of these gates are essentially a version of logistic regression. In fact, it is logistic regression, where your binary outcome is to determine whether or not you keep your information or you forget your information. And this is known as the memory within the architecture. And each of these gates always has a different transform that's associated with it. So the very first gate, forget gate, it's the initial screening, if you want to call it that, where you are just figuring out whether or not to retain that information. And then the next input, which is the input gate, similar activation function, which is usually a sigmoid, and this is also usually a sigmoid, and that's a sigmoid too. But you're essentially just doing another logistic regression based on the associated weights, but there's a little bit additional transformations that are being done. I'll go over that very soon. The output gate, this is the criteria or the gate that determines the final hidden state, and it will just keep on going into the loop. But the most important part is probably the cell state, where it essentially combines the input or the outputs of your forget gate and your input gate, and it's like a weighted sum, and it determines whether or not it will retain your initial state or whether or not your new state based on your input gate is relevant enough to combine with the previous state. So that's essentially what's happening there. And then the very last part is the hidden state, and it leads to prediction. And you're just element-wise multiplying them, the output gate by an activation function, which is usually your tanh, by your cell state. And note that the tanh, this is usually to regularize your data between -1 and 1. That's just how the tanh function sort of resembles. And so let's go a little bit more in depth as to what this architecture is. Let me label out the points over here. So you have your initial cell states, you have your initial hidden state, you have your input, and then you're going to be traversing through this entire diagram. And I'm going to be breaking apart this diagram for further understanding. So the very first part, as I mentioned earlier, is going to be the forget gate. The forget gate is going to be in this section right here, and it's just a cross multiplication. You just have your weights of x to f, where f stands for forget gate, and you have your weight from your hidden state to your forget gate. And then you are just cross multiplying your weights by your input, your weights by your initial hidden state, and there's always a bias layer. And then your forget gate output is going to go up to here, which will be used by the cell state layer down the road. But the next gate, which is the update gate or your input gate, depending on what literature you are reading, same exact thing almost. You will have the exact same multiplication where you have your weights from your hidden to your update gate, and you have your input that you're multiplying by your weights of your x to u, and it's the exact same thing. You're passing it through a similar activation function, which is more or less a sigmoid function. And then that is where there will be some additional business of cross multiplying, but that's later down the road. Let's go over to the output gate, which is going to be the third section over here. Same exact thing. You are just going to be cross multiplying your weights, x to o, h to o, and there's always going to be a bias associated with that as well. So the final step, or the second to last step, is calculating your cell state. A cell state is given by this equation, where your forget gate is going to be, well, your forget gate output and your update gate output are going to be here and here, and you'll just be adding and multiplying the corresponding values. So a little bit more in depth as to what that is. You have your weights from h to t. I just called it your hidden state to tanh. I just called it with underscore t, but this is the second symbol. Well, this is the second symbol over here, where you are cross multiplying your input with a different weight, and you're cross multiplying your hidden state by a different given weight, and you'll be putting that into an activation function here, which is usually your tanh. Note that this equation is actually the exact same equation that you will see in a simple recurrent neural network, and this is the activation function that is used over there. So it's basically like a simple RNN. You're cross multiplying that with your update gate, and you're adding it with the cross multiplication of your forget gate and your initial cell state. So you should see here as the flow chart, where you are multiplying your update gate by your hidden state, well, your simple RNN up here. There's a multiplication, so ut minus the output over here, which is this right here. So ut times your tanh, which is right here, you're adding that to the multiplication of your forget gate and your initial cell state. And then this is where that input goes to. And then that is where your hidden state comes into play, where you are going to be passing in your newly found cell state, pass that into your tanh function right here, and you just element-wise, you're going to be element-wise producting your output gate to the tanh activation function of your cell state. And then the process just continues, where you are calculating a new hidden state, a new cell state, and also you will be predicting a new prediction. And then the cycle continues, however many layers you got going on and however many epochs you got going. So that is essentially the theory behind the LSTM. in this notebook, I'm essentially using the exact same notebook data from my previous videos on RNNs and GRUs. Very similar procedure. I'll just be comparing the different outputs from each other. I think I already ran this, yeah. And so I'm using TensorFlow 2.4.0, so whatever Keras is dependent on that. It's just 2.4.0. And I just loaded all of my typical data science libraries. I set my parameters so that I get larger photos, and that's largely the only difference between this notebook and some of the other notebooks. But I'll actually be using a different data set this time. I'm going to be using Bitcoin because Bitcoin seems pretty hot right now, and it is just skyrocketing. Look at that. If I would have purchased Bitcoin 5 years ago for $430, I would have made close to like just pure money, $34,000. Oh my God, it's really ridiculous. But yeah, so this is going to be the example I'll be using, and similarly to my previous videos, I'll be breaking up my data set into two different sets, where I'll be using this data set for my multivariate time series example, and I'll just be using my returns for the univariate example. So first things first, let's do the returns of, well, let's go through the process of a univariate time series and just compare an LSTM to a GRU to an RNN. Let's check out those returns right here. Quite volatile to say the least. It had some, oh wow, 20% ups, and then all the way down to you can lose like close to like 35% in a day. So incredibly volatile, very risky instrument, so it seems. Let's check out the histogram. It actually looks pretty normal. You can definitely run a statistical test based on the returns to see if it's like a normalized distribution. And then you could probably run some normal, I guess, kernels on that. Interesting. Yeah. Anyways, I'm converting all my stuff. I'm scaling everything downwards, just scaling the returns array. And I have 1830 observations, 5 years worth. And this is what my data looks like. I'm using 10 historical data points to predict the 11th historical data point, and I just reshape all my data so that the corresponding X and Y arrays have the correct inputs and outputs. So once that is done, I'll be converting everything back to an array and then print out the dimensions, see if everything is correct. I'm using 90% as my threshold, so 9% as my training and 10% as my testing. And then I created 3 different functions. I have the RNN example, GRU example, LSTM example. The only thing that's different, I just called simple RNN, GRU, and LSTM. I have 30 units instead of like 10, which my previous videos are, or 3. So it's going to be like a 30 over here. And everything else is pretty much the exact same thing. I have to make sure my shapes are correct. I have a dropout layer, and I only have one node for my dense layer or my output layer, where this is essentially predicting a regression task. Same thing for my other examples over here. So let's run these 3 functions, and I'm returning the model over here. So let's initialize these models here, and these are my outputs. So 991 parameters, 3001 parameters, 3871 parameters. And let's start training this stuff. The same exact thing. It's going to take a little bit of time, but we are essentially just using the exact same code. We are passing in the X values and your Y values. Make sure you do not shuffle, since this is a time series data example. We're going through 100 epochs, 32 batch sizes, 20% for the validation split, and of course print out the outputs over here. So I'm gonna let that run real quick. It shouldn't take that long. Yeah, it's currently running over here. And then once this is finished running, I'll just be printing out the loss functions to see how well they do. And I was looking into trying to combine the runtimes for both the RNNs, the GRUs, and the LSTM all into one block. But I figured it wasn't really good practice to do so, because there might be an error in one of your models, and it's just gonna ruin the entire runtime for all of your other models. And in general, if you want to create your own model, you should have your own box with that. But Yeah, so this is what the training function or the training loss and the validation loss looks like. They are going toward each other, so I guess that looks good. Let's check out what the multi-step forecast looks like. I've been essentially using the exact same code what I did earlier, just some tweaks, obviously. I'll be predicting 3 different models using the same inputs and then just appending those inputs using the sliding window approach. And it will just keep on going through until I'm out of testing observations to test out what that looks like. So I have 182 forecasts to do based on the 1638 training observations. Oh, that's actually my threshold, so I'm not really using that. I'm just using the range. So let that run a little bit. It shouldn't take that long. But yeah, it's essentially the exact same principle of the sliding window approach, where you're appending your latest observation, your prediction, to your inputs, and then you keep on going through. So you're always chopping off your oldest observation and appending your new observations, and then you're just using that to predict your future time steps based on the historical data. So let's check out what that looks like. I printed out what the arrays look like because I usually get a flat line, and it looks like I am going to get a flat line. This is largely, we should largely be expecting this because all the observations are dependent upon one another, and that is what essentially like time series is. And it seems like it's not really even capturing the trend up and down. So this model is not a very good model. We just need more data to capture these ups and downs of the return. So yeah, so let's check out the multivariate forecasting, where we will be using this data set over here. So we have a high, low, open, close volumes, and notice that over here, compared to my previous videos, I just did a percentage change between the days. So this is like a 0.8% increase. This loss 0.2%, and it's based on the close. So this is just the percentage changes based on the high, lows, open, close, and volumes. Same exact thing for the multivariate approach. You're just appending your values to your X and Y arrays, except you are now appending multiple features to your X, and your Y's, you're still predicting the same scalar. So you're going to get something like that, where you have 1, 2, 3, 4, 5 features, which correspond to the high, low, open, close, and volume. That's what that is. And then we'll just keep on going through. Do the exact same thing. Let's print out the dimensions of those arrays. Let's create the train X, train Y, test X, test Y. And let's reinitialize the models, because you need to do this because we have a different amount of features that we are plugging into our model, and our model was trained on just one feature previously. So retrain that, and let's retrain the models over here. So this should take a little bit longer, just due to the fact that we have like a larger amount of features that we are dealing with. But it shouldn't take too long, because we're not dealing with like millions of observations or millions of columns or millions of features that typically drain the resources of your computer. So let's run that, and then of course we'll be plotting the loss iterations, see how well that does over there. So let that run. Notice I'm using the exact same principles: epochs 100, batch size 32, validation split 20%, and just do that for all the models. So machine learning is wonderful, honestly. Like, the hardest part is literally just understanding the data, and also just the architecture in general that you're dealing with, and you can largely just play around with what's already out there, and then just replace some of those activation functions, maybe add a few more layers, and you have like almost a novel type layer. But that takes a lot of money just to train those sort of things and validate those models to see if they're even working. So let's check out the RNNs. So yeah, this actually looks a little bit better because it has more data. Everything's at 1 point, so the loss function looks pretty good. Let's see how well one-step forecast looks like. Of course, yeah, it's still pretty bad. Everything's still it's still predicting like essentially an average, and it's doing different averages for different models, which is to be expected because it's trying to capture the memories the LSTMs and the GRUs. It has different memory sequences, and therefore it will have different averages, I suppose. But yeah, so let's actually take a look at a very deceiving plot. I keep on seeing this, and this probably could be a clickbait, honestly, but I keep on seeing this where I will essentially be just scaling everything, and we will just be predicting the adjusted close, the scaled value, not the percentage change. And this is, I just see this everywhere. I'm still using the exact same methodology on where I am training the models, I'm recreating the data set, but we will just be predicting based on the price structure. So largely just the data itself. There's no transforms. I'm just scaling it, and we will see a very misleading plot. So let that run for a little bit. Sweet. So I let this run for a little bit. It only took like a minute or so. Let's plot out the loss function over here, or just the loss in general, and it looks a little bit better, I suppose. But let's check out the predictions for a one-step forecast, and look how deceiving this is. So this is just a scaled version on what we are working with, but it's essentially largely the same principle. Everything just shrinking down, and we have the true values, which is the blue. I guess if you strain your eyes hard enough, but largely all the models are very indicative on what may happen in the future. And this is actually very misleading because as we saw previously, our models didn't do much of anything. You really just want to be predicting the percentage changes, not the actual value itself, because if we can't even predict the percentage changes, then who's to say that we can predict something like astronomical as this, where you have like a specific price point ahead? So I was doing a little bit of research into this, and largely all the financial analysts or financial engineers, they're always looking at a percentage rate of return, not necessarily like what price you're going to get, because predicting a scale or price is like probably like impossible. I don't know anyone that can do that, or it's not in any literature. So hopefully that this video cleared up any misconceptions about the use of these particular models, whether it be LSTMs, RNNs, GRUs. It comes down to the point of what type of data that you are going to be using for these models, because utilizing its own historical price points to predict its future price points based on just its adjusted closing prices is fundamentally flawed. Because you would have to think that many external events, exogenous factors, play a huge role in the ups and downs of a given price, whether it be a commodity, a stock, a fixed income, that sort of thing. Like if the US government were to ban Bitcoin, then Bitcoin can go potentially to zero. That's just my speculation. Like as we've seen over in China, when they banned Bitcoin, Bitcoin took a dip. I don't really remember when, but it definitely took a dip when it was banned over there. So, you know, on these huge factors, if you could somehow predict those factors, you're golden. You're going to have a great and stellar model. But yeah, if you like this video, please make sure you hit that like button. I'm going to be doing a ton of content related to just neural networks in general. And all these applications are incredibly exciting, and I hope that you are as excited as I am. So I hope to see you in the next one. Thank you so much for watching.